Hello, my good people. Welcome again to my YouTube channel, Odavig Structure Hub. This is a place where you learn, build, and innovate. Today, I want to talk about timber design to BS 5268. And before I can begin designing timber, let's understand a little bit what a timber is, its definition, its characteristics, its uses, factors affecting the strength of timber, and other definition of terms. So let's begin by defining what a timber is. A timber refers to a wood that has been processed and prepared for use in construction and structural application. Characteristics of timber. Number one, we have natural materials. Number two, renewable. Number three is workable. Number four is strong and durable. Lightweight. So those are the characteristics of timber, and they are self-explanatory. So there's no need of taking much of our time elaborating those points. So we have uses of timber in civil engineering. Number one, we have building frames and roof structures. Number two, flooring and ceiling systems. Number three, formwork for concrete, bridges and pedestrian walkways, scaffolding, and railway sleepers. Again, those are self-explanatory points. No need of going much deeper into them. Now, let's talk about factors affecting strength of a timber. So, number one, we have species. So, under species, you can say that different tree species have different cell structures and densities. Example, we have hardwood. Hardwood, examples of hardwood, we have oak and mahogany. So, hardwood are generally stronger than softwood. So, example of softwood includes pine, cedar, etc. And then we go to number two. Number two, we have moisture content. So, under moisture content, you can say that timber strength decreases with high moisture content. So, seasoned dry timber is stronger than is stronger and more stable than green or freshly cut timber. And then moisture causes shrinkage. Again, it causes swelling and it causes decay. And then you have the third one, grain orientation. So under this, timber is stronger along the grain than across it. And then you have the density, which is the fourth one. So then the timber is generally stronger and more durable. So we have the knots and the defect. So that is number five. Knots, split, checks, and insect damage. It reduces the strength of a timber. And then number six, we have the rate of growth. Slow grown timber is stronger than fast grown timber. So that is a self-explanatory. And then the last one, you have treatment and preservation. So treatment and preservation, it improve resistance to insect attack and the moisture attack. So those are the points about factors affecting strength of a timber. So we have others that I have not mentioned here. You can do more research and get to know about them. Definition of terms. Number one, dry stress. What is a dry stress? This is a stress applicable to a material exposed in a condition which will result into a solid timber having a moisture content not exceeding 18% in service. Number two, wet or green stress. This is the stress applicable to a material exposed in a condition which will result in a solid timber having a moisture content exceeding 18% in service. And then number three, we have the grade stress. This is the stress that can be permanently sustained by a material of a specific section, size, strength class, species, and a grade. And then we have strength class or SC. So this is the classification of timber based on a particular values of grade, stress, modulus of elasticity, and the density. Modification factor or K. These are factors used to modify the grade stresses as a result of service, duration of loading, load sharing, etc. Definition number 6. Permissible stress. So this is stress that can be safely be sustained by structural materials and at a particular condition. It is a product of grade, stress, and appropriate modification factor for section size, service class, and loading. And then we have number 7, glued laminated timber, or in short we call it glulam. So this is a structural timber member with a number of lamination glued together with the grain of lamination essentially parallel. And then we have the last one, basic stress. So this is stress that can safely be permanently sustained by timber containing no strength reducing characteristics. Knot area ratio. So what is a knot area ratio? It's the ratio of the sum of the projected cross-sectional area of knots to the cross-sectional area of the piece. So in simple term, it's the ratio of cross-sectional area of the knot you divide by the ratio of cross-sectional area of the piece. And what about strength ratio? So strength ratio is the ratio of the strength of a piece of a timber with a defect to strength of the same piece but without a defect. Then we proceed to stress grading. So how can you grade timber based on their stress? Number 1, we have visual grading. So this is a manual process carried out by approved graders who have been trained and have demonstrated their proficiency in techniques. So the graders examine each piece of timber to check whether the size and the frequency of the specific physical characteristics such as knot area, resin pocket, slope of grain, wane, rate of growth, and distortion. So these are compared with permitted limit given in the code to determine whether these are accepted in one of the visual stress grades or rejected. So the two visual grades referred in the standard are number 1, general structural stress or GS, and number 2, specific structural grades or SS. Then we have the second grading of timber is machine stress grading. So this method is based on the principle that strength is related to stiffness. Stiffness is established by measuring deflection under a load without destroying the test piece. Timber specimen is passed through a stress grading machine and by means of series of rollers. Some are static and some are exerting pressure. So bending is induced at increment along its length. The resulting deflection is measured by a computer linked to a machine which compares the strength characteristics with the programmed parameter in the computer. So the accepted timber falls into one of the 4 machine grades. We have the MGS, the MSS, M50, and M75. Let's talk about modification factor. So number 1, you have the duration of loading or K3. So for how long are you going to load your structure? For example, long term, medium term, short term, very short term, etc. So duration of loading. So modification factor for duration of loading K3 is shown in table 16 of BS 5268. So this is table 16. So anytime you will be designing timber, you will need this table for the modification of factor for duration of loading or K3. So we have duration of loading, and then on the other side, on the right hand side, you have values of K3. So if we can start by number one, we have long term. Example of long term, we have dead plus permanent imposed. So the modification factor will be 1.0. And then number two, we have medium term. Example, dead plus no or dead plus temporary imposed. So the modification factor is 1.25. And then we have the third one, short term. Example, dead plus imposed plus wind, or dead plus imposed plus wind plus no. So that is 1.5 for values of K3. And then we have the last one, very short term. Example, dead plus imposed plus wind. So the value for K3 is 1.75. So something to note, K3 applies to all grade stresses. Example, bending, shear, and compression grades. Let's talk about modification number 2, which is notched end or K5. Notches at the end of a flexural members will result into high shear concentration, which may cause structural failure. So this is type of notch, and it is at the top edge. So modification factor for this type of notched end is this one. K5 is equal to H into bracket HE minus A, close the bracket, plus AHE. Then you divide by HE square. For A is less than HE. For if this distance is less than this one, we use this formula. But if A is greater than HE, then K5 will be 1.0. So under notched end, we have number 2, notch on the underside. So this is the notch on the underside. So the formula for K5 is equal to HE over H. So HE over H. And K5 should be greater or equal to 0.5. So the point to note, K5 only modifies the grade sharing stress. So it only modifies the grade sharing stress. Modification number 3, we have depth factor or K7. So the grade bending given in the code, that is called BS 5268, apply to the timber section having a depth of H of 300 millimeter. For other depth of beam, the grade bending stress is multiplied by a depth factor K7 defined in BS 5268 as follows. So K7 is equal to 1.17 for solid beams having depth less than 72 millimeter. And then K7 is equal to 300 over H raised to power 0.1 for solid beams with depths H is greater than 72 millimeter but less than 300 millimeter. And then we go to K7 is equal to 0.81 into bracket H square plus 92 300, close the bracket, you divide by H square plus 56 800 for solid beams with H greater than 300 millimeters. Modification number 4, we have load sharing system, that is K8. So the grade stresses given in table 9 of BS 5268 applies to individual members. Example, isolated beams and columns rather than assemblies. So when four or more members such as rafters, joist, column are specified at a maximum of 610 millimeter center to center, then they act together to resist the column loads. In case where the spaces is less 610 millimeter center to center, all the grade stresses should be multiplied by a load sharing factor K8, which has a value of 1.1. We start now timber beam design. So the following design consideration are checked. Number one, you have bending. So bending is based on the theory of simple bending equation. This is the simple bending equation. M over I is equal to F over Y is equal to E over R, where M is equal to moment of resistance of section and I is the second moment of area. F is the fiber stress in bending, and then Y distance of extreme fiber to the neutral axis. E is the Young modulus of elasticity, and R is the radius of curvature. From the equation above, we can have M over I is equal to F over Y, whereby F, you can make this F the subject of the formula. So we'll cross multiply this and this, and then F is equal to M over Y. Now F is equal to My over I. We have seen F is equal to My over I. Also, Z is equal to I over Y. So Z is the section modulus. So the formula for section modulus is I over Y. And F is equal to M over Z. Because if you can replace this Iy into this formula, we'll have F as equal to M over Z. So Z is equal to M over F. So you make Z the subject of the formula. So this is the design formula for timber beam. So for a rectangular section, Z is equal to BD square over 6. And BD square over 6 is equal to M over F. As we have seen, Z is equal to M over F. But Z is equal to BD square over 6. So that is it. So if F is the permissible bending stress in timber parallel to the grain, then equating maximum bending moment to the suitable size of timber joist when depth over breadth ratio is known, and number two, when either breadth or depth is known. Design consideration number two, we have shear. The maximum shear stresses in a loaded rectangular beam section is given by, this is tau is equal to 1.5 V divided by BD, where V is equal to maximum shear force and B is the breadth of the section. D is the depth of the section. The maximum shear stress induced must not exceed the permissible shear stress in a timber parallel to the grain. We come to number three, design consideration, bearing. The bearing stress at the support of the joist is given by, so Q bearing is equal to V over Bx, where V is the maximum shear force, B is the breadth section, and X length of bearing. The bearing induced must not exceed the permissible stress in compression perpendicular to grain in timber. So design consideration number 4 is deflection. The maximum deflection is calculated using the appropriate deflection formula for the respective loading case. The total deflection is the sum of the bending deflection and the shear deflection. So in bracket, this is the total deflection is equal to deflection in bending plus deflection in shear. So the first case is this one. It's a simply supported beam loaded at the center. So the total deflection is equal to, this is the formula for this. So the whole of this is the bending deflection and this one is the shear deflection. So the first case, this is the formula. The second case is a simply supported beam with a UDL. So the total deflection is this. You use this formula. So the third case is this one. So this one is a cantilever beam with a point load at the far end. So the total deflection is this formula. And the final case is a beam loaded with a UDL. So the total deflection is WL over 4 over 8 EI plus 48 WL square over 5 AE. So that is it. And we will use these formulas in our proceeding examples. For solid timber members acting alone, i.e. space that is more than 610 millimeters center to center, deflection is calculated using E minimum. So the keyword is E minimum. But for the load sharing system, the deflection should be based on E mean. E mean is the keyword. Effective span. This is the last subtopic I will be talking about. So effective span. For a simply supported beam, the effective span is taken as the distance between the center of bearing. So this is the beam. It's a simply supported beam. And as you can see, this is the wall and this is the wall. So the distance, the internal distance from wall to wall is clear span. And the distance from the center of the wall to the center of the wall is effective span. And the distance between the outer walls from here to here is the actual span. So the effective span is equal to clear span, which is this distance from here to here, plus one bearing span. So one bearing span is this distance of this wall from here to here. Or clear span plus, this is the clear span, plus a half times one bearing, a half times one bearing, this is one bearing, and then you multiply by 2. You will get effective span. This is for a simply supported beam, and number 2 is a cantilever beam. For a cantilever beam, the effective span is equal to clear distance. This is the clear distance from here to here, plus a half bearing. So this is the bearing. So plus a half bearing, a half of this distance of the wall. So in my next session, I will start designing timber beams.